So we can start our topic, that is magnetic dipoles. So in magnetic dipoles, first let us revisit some basic ideas and we will solve some problems related to magnetic dipoles. So magnetic dipoles. So first thing is that the basic idea is, if we are considering a current carrying loop, let me consider a current carrying loop, and let's say current is flowing in clockwise direction. This is clockwise direction. Or suppose let's say current is flowing in anti-clockwise direction. This is anti-clockwise direction. So in this case, we can define the dipole moment, and the dipole moment will be given by I vector is equal to m vector equal to I into a vector. This is my dipole moment. So here the current is flowing in phi cap direction in the basal plane, and using right hand rule we can find the direction of the dipole moment. That is very easy thing that we will discuss. Let's say this loop is having certain radius, let's say r, and this radius is very small. This r is small. That means we are considering a small current carrying loop. When I'm saying a small loop, that means R is very, very small. In that case, whenever current is flowing, we can define the dipole moment. This current carrying loop actually behaves like a magnet, and this magnet will have certain dipole moment that we can see in this page. Let's say I'm having a current carrying loop, anti-clockwise direction I'm taking. So what is happening here, this loop is there, and we can show the magnetic fields due to this current carrying loop. And you can see here the current is going inward, and here the current is going outward. It is coming towards my side. Inward in sense it is going to the screen side. So here we can show the magnetic field lines, and this is inward. So inward in sense the field lines can be drawn as clockwise. So here we can show the field lines as clockwise. Here the current is going outward. So here we can show the field lines to be anti-clockwise like this. And here in these 2 points, here we can show that field lines are going what? Out of the plane. That means it is outward only. Outward. And this exactly show a picture that we can draw for a bar magnet. If we show a bar magnet, let's say I'm drawing a bar magnet. This is my north pole, this is my south pole. So this exactly, so there will be a bar magnet which is present here, and the fields are coming like this, from north pole to south pole, then from north pole to south pole, and here from south to north. So this form a closed loop exactly like this. We can show, you can see this is a magnet which is present here, and the lines are going from north pole and they're entering into the south pole. And here you can see from north pole the lines are going, magnetic lines are going from north pole entering into the south pole, and here the lines are going from like south to the north pole, like that. North pole to south pole, and then basically south pole to north pole. This forms a closed loop, right? So here also north pole to south pole, and then is basically the lines of force coming here like this, and then it's going from, let's say, the south pole, this is north pole. So north pole is starting from north pole entering into the south pole, then basically going from south to north pole like this, south to north pole. Here also same issue, north pole to south pole, and then basically what? Then basically south to north pole. So this shows that this current carrying loop is behaving like a magnet that we have drawn here, and this magnet is having certain dipole moment, and that dipole moment is given by I into area, and the direction of the dipole moment the direction of the dipole moment. We can find the direction of the dipole moment using right hand thumb rule. This is right hand thumb rule. We can apply this rule in order to know the direction of the dipole moment because it's a vector quantity. So this is the basics ideas that we have discussed. We can do some problems in order to understand this concept. So first problem that I can consider is a hydrogen atom. Hydrogen atom. Let me consider a hydrogen atom. And the radius, let's say I'm considering the nth orbit of the hydrogen atom. Nth orbit. So nth orbit in sense the radius will be Rn, and the electrons which are revolving in the nth orbit having speed equal to Vn. So what will be the electron speed? Electron speed is Vn. So these are the electrons. So let's say these electrons are moving in anti-clockwise direction with speed how much? Vn. So obviously conventional current will be in opposite direction. In that is in anti-clockwise direction, electron in clockwise direction. So this is Rn. So we have to find the expression for the dipole moment in vector if this is the situation. So what to do in this case? It's very simple. Dipole moment is basically, if you say the magnitude is basically I into A. What is I? I is nothing but the rate of flow of charge. So it will be E by T, and T is basically in this case distance by velocity, and distance is basically 2 pi Rn, and velocity is Vn. So 2 pi Rn and velocity is Vn. So it will go up, and area is basically pi Rn square. So pi and pi will get cancelled, 1 Rn will get cancelled. So it is E by 2 Vn into Rn. This is the dipole moment, and we can simplify it, and we know from Bohr quantization, from Bohr's quantization, this angular momentum L is given by mvn Rn is equal to nh cot, and this Vn Rn is nothing but nh cot by m. So we can substitute there, and we can find this m is dipole moment, this m is the mass of the electron. So don't get confused. So m will be, dipole moment will be E by 2. Vn Rn is nh cot by me, and this is the expression. And we know the radius Rn, it can be written in terms of Bohr's radius, because A0 is my Bohr's radius, which is given in the question. Bohr's radius, which is given. We know Rn expression 0.53 like that, n square by z times angstrom, right? So this n, this z is equal to 1 for hydrogen atom. So 0.53 n square angstrom, and 0.53 is nothing but what? It's my 0.53 angstrom is nothing but my Bohr's radius. I can write A naught. So this will be A naught times n square. This is Rn. A naught is nothing but 0.53 angstrom, and that we can write, and n equal to 1, 2, 3, that we can get, and we can find the radius in terms of angstrom. So A naught times n square, and this n square will be given by Rn by A naught, and there will be a square root if you find n. So we can write here finally the expression E by 2, and this is square root. All the constants I can take outside, EH cot, and this is ME, and this will be square root Rn by A naught. And A naught is a constant, that is 0.53 angstrom, like that I can say. And this dipole moment will be depending on square root Rn, and this is a z cap. Since current is in phi cap direction, dipole moment will be in the z cap direction as per the right hand thumb rule. I hope this question is clear. Let us go to the second question. The second one is, let me consider a disk of some radius, let's say capital R. I'm considering a disk, circular disk of a radius R, and this is carrying a surface charge density, and that is uniform surface charge density. Let me mention here, spell out here, uniform surface charge density, which is sigma, right? And this is a rotating disk. This is a rotating disk. Rotating disk, which is given in the question itself. And this rotation is happening with a certain angular velocity. Let's say that angular velocity is omega. Angular velocity is omega. Okay. So now it has been asked to find the dipole moment. Find magnetic dipole moment. So let me consider the disk. Okay, let me draw here. So this is a disk which is given. The radius is given, capital R. All this stuff I can show. And here we are having a uniform surface charge density. That is clearly written here, uniform surface charge density. Not any case we are discussing about non-uniform charge density. Okay. So since this disk is rotating with certain angular velocity omega, so the surface charges which are accumulated, they are also rotating. That is well understandable. Whatever charge will be there in the on the surface, since it is a rotating disk, so obviously these charges are also basically rotating, right? And since the charges are rotating, so there will be current which will be set up in the phi cap direction itself, because rotation is happening in the phi cap direction. That is my basal plane, and the dipole moment will be in the z cap direction. But the question is here, the surface charge density we can write is charge by area, right? Charge by area, q by a, like that I can write charge by area, or q I can write sigma times a. So in order to find the dipole moment, I can consider an elemental ring, and due to the elemental ring, I can find the dipole moment. That will be the elemental dipole moment, and I can integrate to find the entire expression for the dipole moment. So let me consider an elemental ring. This is an elemental ring. I'm drawing it like this. This is the thickness of the elemental ring. The thickness is given by, let's say, dr. The thickness is dr. So what will be the thickness of the ring? The thickness is dr. Okay, this is the thickness. The thickness is given by dr. Okay, and this radius of the elemental ring is smaller. So for entire part, you have to integrate up to capital R. So that is well understandable, and we know magnetic dipole moment is given first magnitude, then we will show the direction I into a, and I is nothing but dq by dt, rate of flow of the charge. So I can find the expression for current I equal to dq by dt, and here the charge is given by sigma times what? Sigma times area, and the area in this case is 2 pi small r into the thickness. So 2 pi small r into thickness. And the time, what will be the time? If omega is the angular velocity, so omega is basically 2 pi by t, so t is equal to 2 pi by omega, or dt equal to 2 pi by omega. Here we are not considering t, we are considering dt, very small time interval. And the charge which are accumulated on this elemental ring, elemental means very small ring, is radius is r, small r, and that is small r is very small. So that's why I am saying elemental ring. So there will be elemental dipole moment, and the charges which are there on the elemental ring is basically elemental charge. So elemental charge will be given by dq. Dq means very, very small charge. Dq, very, very small, infinitesimally small. Infinitesimal, you can say infinitesimal. Infinitesimal means very, very, very small. So we are considering very, very small charge which are accumulated on the surface, and this small charge is given by dq, and the charge density is sigma, and dipole moment is also elemental. So elemental dipole moment means moment is very, very dipole moment is very, very small, since it is a small ring, or you can say elemental ring, like elemental area we will discuss, very, very small. So the small dipole moment will be what? Elemental dipole moment. Elemental dipole moment. So elemental dipole moment, it will be given by dm. Whenever there is d, that means very, very small. Okay, so dm is basically I into area, right? So here the area is basically what? Here the area we have to consider. Area is basically pi small r square. So that thing should be very much clear. Pi small r square. All these things are multiplied, and I, we got now the expression for I. This omega, this 2 pi can get cancelled. Very simple expression will get sigma times omega r dr. Just we have to substitute this expression in this expression. So upon substitution, sigma times omega r dr, so it will be r q dr. It's very simple. And for the entire dipole moment, so entire dipole moment, that is m, that can be given by integrating this. So m vector will be sigma omega, and integration will be 0 to, limit of integration will be 0 to capital R, because integration variable is R. Integration is done with respect to R, right? So RQ dr, that means integration is done with respect to R. So upon integration, we can write the entire expression to be R4 by 4, and this will be Z cap. This is the correct expression. I hope this is clear to everyone. Now we can discuss some advanced type of problems where we are going to use different symmetric system. Like we have discussed cylindrical polar symmetry, spherical polar symmetry, and all these coordinate systems are well used whenever we find the problem in that particular system, or we use this particular system upon our convenience. So let me start with the cylinder. This is my example 3. So I'm considering a uniformly charged. I told you before also, we are discussing everything about uniformly charged materials. So uniformly charged cylinder, charged solid cylinder material, solid cylinder, and this is also a rotating one. Since rotation, then phi cap, all these stuff we have discussed here also. So this is my cylinder solution. Solution I can write here. So this is my cylinder. And yeah, so this is basically the rotation which is happening. This radius of the cylinder is given by r. Yeah, so the radius is given by capital R. This is r, this is r. So radius is r, and obviously the charges which are there, that is inside the volume, we are having the charges, and the height of the cylinder is given is let's say capital M. That is good. Let us find the dipole moment. So charges are there inside the volume. So this is a rotating cylinder, solid cylinder. So here the charge density rho can be written as charge by pi r square L. So this is my charge density. So now what I can do here is I can consider an elemental volume. So if I am considering a elemental volume is very, very small, and that is given by d tau or dv, whatever may be. I know I told you before also, whenever we are writing d means it indicate it is very, very small, and we will be having small charge in sense we will be representing that in dq, not in q. We will be representing that in dq, very small charge or very, very small charge, and that is dq. And we will be having elemental dipole moment, very, very small dipole moment, that is dm. And for the entire dipole moment we have to integrate. These are the exercise that we are going to do right now. So let me consider a elemental volume. This is my elemental volume d tau or dv, which is there or situated at a location, there's a small r, and this d tau in the cylindrical symmetry system r dr d phi dz, if I remember. Yeah, r dr d phi dz. So now we will be doing some mathematics, nothing else. So what will be the current? We can find the expression for current. It is dq by dt, and dq is nothing but rho d tau, and this is my omega will go up, and this is 2 pi. So what is d tau? D tau is the volume element we will be considering in the cylindrical symmetry. So I will be omega rho by 2 pi, and d tau is given by r dr d phi dz. So you can see this will be having a triple integral because it is having r part, phi part, and z part. So integration is done with respect to r, phi, z, triple integral. So we will be doing triple integral here. So now the expression for the dipole moment, we know elemental dipole moment due to this elemental volume is d tau. Here I have written, this is my elemental volume. So this elemental volume will be having elemental dipole moment. Okay, so we have considered an elemental volume. This elemental volume will be having elemental dipole moment. So what will be the expression for elemental dipole moment? So elemental dipole moment is dm, which is very simple. If you write dm, so dm is what? Dm will be I times area. So I is given by this expression. So we can substitute the expression omega rho by 2 pi, and this is r dr d phi dz, and the area that we will be taking is basically what? This is the expression. Area will be pi r square. Pi r square. It is the area. Yes. So these are the steps we have done, and now just we can cancel pi part. So this we can do very simple, and now integration, nothing else. Pi will get cancelled, and what else? Nothing. And r square will give you r cube. So we can write dm to be omega rho by 2. This will be r cube dr d phi dz. So for entire dipole moment, we have to integrate with respect to r, with respect to phi, with respect to z. And here the limit of integration for r is 0 to capital R, and for phi it is 0 to 2 pi, and for z it is 0 to capital L. Let's say this part is my L, right? This part is L. Let's say this is my 0, this is my, let's say, L. Correct? And this will be giving me the height of the cylinder. And the height is basically here in this case I have considered it is L, capital. So now just integration omega rho by 2 r q dr d phi dz, omega rho by 2. So m will be integration 0 to capital R, 0 to 2 pi, and for z part, for height part, it is 0 to capital L, and the expression was omega by 2 pi. Let me go here. Omega rho by 2 pi r q dr d phi dz. Omega rho omega rho by 2. So I can take this outside. These are constant. Omega rho by 2 r cube dr d phi dz, right? R cube dr d phi dz, omega rho by 2 dr d phi dz. So now the integration is very simple. When you are doing integration with respect to r, all these parameters will be treated as constant, and just we will be concentrating on this part, then phi part, then z part. So it will be giving me omega rho by 2, and this will be r to the power 4 by 4, and for the phi part it will be 2 pi, and for the z part it will be l. All are multiplied. These are multiplication, right? So obviously this is very simple. 2 will get cancelled here, and this is what? Omega rho omega pi rho l r to the power 4 by 4. So this is my m. These are multiplication. 4 will be in the denominator. Only 4 is left. So this is dipole moment. This is, and one can find in terms of charge also. If in question it is asked to find in terms of charge, the thing is to be done. Just use this expression pi r square r. This is the expression that has been given. So you just q is equal to pi r square l into rho. Just substitute this in this expression, and we can find dipole moment in terms of charge q, right? That is basically in terms of charge q, because whatever charge that is given, that is inside the volume, and this is my volume current. This is going to give me volume current, right? Because whatever current, whatever charge you are giving to this cylinder, this is a solid cylinder, so whatever charge you are giving to this cylinder, this charge will be accumulated inside the volume, and there will be a volume current will be set up. So now we can discuss about the cell, spherical cell. So this will be my example number, I think it is example number 3 or 4. Yeah, 3. Very nice, 3. So example number 4. So let me consider a spherical cell of radius capital R, and sigma is the surface charge density. Sigma is the surface charge density, and this is the diagram. We have to find the dipole moment as usual. I'm not writing again and again that we have to find dipole moment. This exercise is all about to evaluate dipole moment. I hope after watching 3 problems, things might be clear. So this is my cell. So whatever charge you are giving, that will be accumulated on the surface, and you will be having sigma, the surface charge density, because it is a cell. So the cell is having certain radius, and that the radius is given by r. So here in this case, what we can do, we have to consider a elemental surface element. We have to consider surface element. Okay, surface element, like earlier we have considered volume element, right? Volume element, that is d tau, or elemental volume, whatever you say, elemental volume, or you say it volume element, does not matter. It is very, very small, d tau. Okay, similarly elemental area, or you can say surface element, or area element, whatever may be, or elemental area, whatever may be, elemental area, or simply you can say basically area element, same thing. It is dA. These are vector thing, so it will be on the surface only. So on the surface means what? On the surface, in sense, the radius or the separation will be r, right? This is on the surface, the surface element, whatever you are taking on the surface in three-dimensional view. So this is theta, this is theta. So what will be the radius of the elemental ring? This will be my elemental ring, which will be there in the here. So I can draw it separately also. So this elemental ring will be given by elemental ring. In previous case, we were having an elemental volume, and obviously the area we have written pi r square, whatever may be, d tau was the elemental volume, and due to that elemental volume, the elemental ring was having radius r, so pi r square we were using. But here in this case, the radius of the elemental ring is not capital R, it is basically capital R sine theta, right? Because very simple, this is r cos theta, so this will be r sine theta, correct? R cos theta, one component will be coming, another component is r sine theta. So this is r sine theta. So this is the elemental ring. For this, we are having the elemental dipole moment, and the elemental dipole moment will be given by dm is equal to I area. Area is pi r square sine square theta. And this I we have to, I is nothing but dq by dt, that we all know. So I equal to what? dq by dt, and where dq is charge times of area, dA, and dt is basically 2 pi, and those omega will go up. So what will be the surface element in the spherical symmetry? If you remember, the surface element, since for the surface element r is constant, it is fixed, so the part which is changing is theta and phi part. So it is r d theta, r sine theta, d phi. So it is nothing but r square sine theta d theta d phi. So this is my area element, right? This is my area element or elemental area, whatever may be. So we can substitute here and we can write omega sigma by 2 pi. It is r square sine theta d theta d phi. And what was the expression? Dm. Dm was I will be omega sigma by 2 r square, and there was also r square, right? Pi r square, pi got cancelled, r square sine square theta, it will be r4, and this will be sine q theta d theta d phi. So what will be the entire expression? Just integration we have to do, and this integration will be 0 to what? Theta. Theta is 0 to pi, because integration is only with respect to theta and phi. All the parts we can take outside. Omega sigma by 2 r power 4. So it's sine q theta d theta, and phi part is 0 to 2 pi, and this is sine q theta d theta and d phi. So omega sigma by 2 r to the power 4. So sine q theta d theta integration we can do. So m will be how much? So m will be omega, what was the expression? Let me check again. Omega sigma by 2 r to the power 4. Omega sigma by 2 r to the power 4, and just integration sine q theta d theta, and phi part was there, right? D phi. Yes. 0 to pi, 0 to 2 pi. So I'm not doing this integral sine q theta d theta 0 to pi. It is well known to us. We can do it, and that directly I will be writing the expression sine q theta d theta integration, limits of integration 0 to pi is simply, we can write, it is basically 4 by 3. Yeah, this can be reached, this can be verified. So if you are doing so, omega sigma by 2 r to the power 4, so this is 4 by 3, and this is another 2 pi will be coming. So 2 will be getting cancelled, and 4 by 3 omega sigma r to the power 4. This is m vector, and direction is z. I hope this is clear. Another problem, this will be my last problem, And this is also a very simple question. That's example number 5. In this case, we are going to consider a solid sphere. A solid sphere. So whatever charge you will be giving to the solid sphere, the charge can accumulate inside the volume of the sphere, and you will be having a constant or uniform volume charge density, right? So solid sphere of radius, let's say capital R, and its volume charge density is rho. All these stuffs are given in the question itself. So what do we have to do? We have to find the dipole moment. This is the question. So this is my solid sphere, and I can take the solution. And obviously it is a rotating one. Otherwise the discussion is meaningless. If there is no motion of the charges, no current, and no dipole moment. No current in sense means what? I equal to 0. So I can consider the solid sphere of radius capital R, and whatever charge is given, that is inside the volume of the sphere. And already I told you, since it is a rotating one, it's a rotating one, so charges inside the volume also rotate. So we will be having volume current, correct? Volume current in phi cap, because charges are there inside the volume. That's what I want to say. And this is rotating with a constant angular velocity, because if there is no rotation, there will be no current. If no current, then dipole moment is 0. No current in sense I equal to 0. Okay. So volume current in phi cap direction. So what I can do now is charge density rho is given by charge per volume. This is understandable. So here I will be considering a volume element. Here I will be considering a volume element inside it, which is, let's say, at a distance of small r, and this volume, let's say this angle is theta. This angle is theta. So what I can do here is that I can, this is also what? This is also r, no problem. So basically what I can show is that the elemental ring that is formed in this case is basically r sine theta, small r sine theta, right? So what will be the elemental ring? Elemental ring area, it will be pi r square sine square theta. I think I'm correct. Yes. So pi r square sine square theta. So due to this elemental ring, what will be the dipole moment? The dipole moment will be given by dm, and here the volume is nothing but the volume of the sphere, which is q by 4 by 3 pi capital R cube. That is also clear. So what we can do, we can write the elemental dipole moment, that is dm directly. Okay, it is basically I into area. Area is pi r square sine square theta. So pi r square sine square theta. Now the task is to get the current. So previous problem, as like previous problem, I will be writing here dm equal to I times pi r square sine square theta. What is I? Simply you can write dq by dt, and this dq is basically rho d tau, and dt is basically omega will go up, and this is 2 pi. So this is what we have done previously also, but there was surface current, and this is your volume current. Okay, IV in sense it is V stand for volume, I stand for current. Okay, V here stand for volume, and I simply stand for, or I represent simply, or I is what? Current. So this is my volume current. So rho d tau, rho by 2 pi. What is d tau in case of spherical polar symmetry? It is basically, I think, dr r d theta r sin theta d phi. So we can multiply all these things, and we can have r square sine theta dr t theta t phi. This is the thing we can write, volume current. Now we can substitute in the equation. Dm equal to pi part will get cancel, omega rho by 2, and this is basically what, r square. uh, R square, another r square is also there, so it will be r to the power 4. So it is r to the power 4 sine q theta. Okay, sorry, sine q theta d theta. Okay, sine q theta d theta, and this is dr is also there, dr d phi, and just we have to integrate. It is a triple integral, correct? So for m it will be a triple integral, and this omega rho by 2 can come outside, and it is 0 to capital R, where R is the radius of the solid sphere, rotating sphere, and theta is 0 to pi, and phi is 0 to 2 pi. So this is r power 4 dr sine q theta d theta, and this is d phi, right? So basically, whenever we will be doing integration of this, all these parameters we will be treating it as constant. And what will be the integration part? So m equal to omega rho by 2, so it will be r to the power 5 by 5. Sine q theta d theta integration is 4 by 3, right? So you can directly write 4 by 3, 0 to pi, and d phi part is sine q theta d theta integration, and integration limit is from 0 to pi, 4 by 3, and d phi it is 2 pi, correct? So now this 2 can get cancelled, and this is what, 4 by 3 omega pi rho, and basically r to the power 5, and here also 5 3, it is 15. Directly you can write 15. Directly you can write 15. So this is m vector. So 4 by 15 omega pi rho r to the power 5 set cap. So these are the expression, 4 by 15 pi rho omega pi rho r to the power 5 z cap. So this is the correct expression that we have got. So all these things we have discussed about the dipole moment.